Hello everyone and welcome to the third part of our SCoBi Signal of Opportunity Coherent Bistatic Scattering Model tutorial series. In this video we're going to be talking about how to set up the SCoBi GUI to perform an analysis of a P-band signal of opportunity traveling through a forest canopy. So our outline for this video, we're going to be discussing the problem statement, the problem defined in our user manual for SCoBi. We're going to talk about how to create the input vegetation files for this particular kind of simulation, as well as the configuration input files in the GUI window. Now, in the previous video, I discussed a lot of the visualizations that you might need to consider whenever creating things like the vegetation input file and the configuration input file. And if you're having trouble understanding some aspects of those, I would suggest that you go back and take a look at the second video if you don't mind. But without further ado, let's look at the problem statement. So for this problem, again, we're going to be looking at a forest canopy. So we're going to again assume the vegetation cover for our SCoBi simulator. We're going to be looking at a variable P-band signal of opportunity transmitter, and our antenna pattern for this problem is going to be user defined. So we're going to get to look at the case where all three inputs are going to be required for SCoBi. Again, we're going to be using snapshot simulation, and our ground structure is going to be a single layer. And that's it for this part of the tutorial. We're going to hop straight into the Excel files and then go into the GUI input. So we'll see you right back. Hey everyone, we're back and I am ready for us to take a look at the vegetation input file for this particular problem. So first off, while we're in the source file, we're going to go into the input folder and then the vegetation file, and we're going to be looking for the default vegetation input file for a forest canopy. So we'll click on that. Again, this thing is going to open up with two sheets inside this spreadsheet where we have layers and kinds. Again, layers is used to define the position of your scatters within a vegetation layer, and the kinds is used to represent the scatterers themselves. So again, the order is what's important, so be sure that layers is first and kinds is second. You don't want the simulator to screw that up. Here in this problem we have 4 different layers, and each of these different layers combine values in different ways. We'll take a look at the kinds sheet. In this problem, we're defining L1 as a leaf, a branch, 4 different kinds of branches, and a trunk. Again, we have our particle density to show how many of these different scatters are in a cubic meter. The dimensions for a leaf are defined in the semi-major, semi-minor, and thickness of that ellipse. The cylinders, which are the rest of the components, all show the radius and the height of that cylinder. EPSR represents the real component of the dielectric constant, while the imaginary portion of the dielectric constant is represented with the next variable. And the begin and end angle are used to calculate the average angle as your vegetation varies from the zenith axis. So each of these values describes some variable, L1, B1 through B4, and T1. And again, these values are inserted into the forest layer through the use of the layers spreadsheet over here. So on the top layer, we have the leaf structure that we define, as well as the 4th branch here, which I believe is the smallest of all of these branches. Yes, that looks like it's correct. No, it's actually a little bit. No, it's definitely the smallest. So the smallest branches are on top, as you would kind of expect, and as you go down, things start mixing all together, where finally at the bottom you have the base of the tree with the trunk itself. So all these things are going to be combined together, and SCoBi is going to calculate a homogeneous vegetation layer based on the definition of your tree canopy that you've described here. All right, so now that's covered, so we can now move on to take a look at the configuration input file. Hey everyone, we're back and we're ready to take a look at the configuration input file for this particular problem, the P-band signal of opportunity through a forest canopy. So let's go back into the input folder, configuration folder, and take a look at our specific default input file. So since this is a snapshot simulation that is using a single layer soil moisture profile with a varying transmitter position, we're going to be taking a look at this default input because it lists all that in the name of the file. So opening this up, we see that again there are two sheets here, dynamic for values that change and ground for values that remain relatively constant. So we're going to take a first look at dynamic. Again, the sheet number is important. So this configuration currently works with dynamic being the front. You move it to the back, things get wonky. So keep your dynamic files at the front. Very important if you're making things from scratch. Okay, so first row is your variable names again. You can change this to whatever you want. We're going to keep it the same because it's for you. You want things to make sense. Our first column, our first two columns actually, since we said that the transmitter is changing its orientation, we need to define those values first. So here we have things defined from 10 to 70 degrees for our incidence angle. And over here we have things defined as 15 to 25 degrees for our azimuth angle. The RMS height of our soil moisture profile, or our ground profile, is ranging from 0.5 to 1 to 1.5 centimeters. And finally, we are varying our volumetric soil moisture from 5% all the way up to 40%. Now the values that you see here will all be combined with each other in some sort of way, such as, say, first we're going to take a look at 10, 15.5 in this column, and then 5% here. And then maybe for the next iteration, well, I guess I should point out that there are no iterations. We're taking advantage of how MATLAB operates, so this is just one giant matrix. But for the next value in the matrix that's used to calculate these values, you might have 10, 15, 0.5, and then 0.1. And then you go all the way down the line. So combining all of these values, we'll see that we would have what looks like is 7 times 2 values in the second column times 3 in the next times, I believe, 8 in the next. That comes out to be 336 different combinations. So this is really great if you're wanting to combine a whole lot of values from a single spreadsheet, from a single sheet, from a single page. It saves a lot of effort from having to do that using the time series mode of having to draw out all 336 different combinations by yourself. Okay, so ground sheet. This defines things that are constant throughout the soil moisture profile through that ground structure. In this case, our sand ratio is defined to be 80% or 0.8. Our clay ratio is 0.07 or 7%. And our bulk density is 1.25 grams per cubic centimeter. So that about wraps it up for the configuration input file for this problem. Next, we're going to be taking a look at the antenna input pattern. So stay tuned for that. Hey everyone, so we're back to take a look at the antenna pattern input file for this problem. Let's go into input and into the only folder that has anything related to this with the single Excel input file, default antenna pattern. So here we can take a look at this kind of spooky at first value. The spreadsheets. We have 4 different sheets that represent the polarization at a given port, cross polarization at that port as a result of another port, and then the second port and its cross polarization that you see as well. So this one is the copolarization of port X, and GNYY is the copolarization of port Y. So, if you take a look at this spreadsheet, if you take a look at the sheet, we have values running along the column axis. You can look here in Excel, we have 61 of these, and if we look at the other side, we've got 121 values going down. So the theta values are being represented by the columns, the ones that have 61 values here. And with those, we have, as I said, 61 points. So we can calculate our resolution, if you will. So for theta, we have 180 degrees in total, because we are ranging from 0 to 180. That means we're going to have 180 plus 1 points. We have 61 points here. We'll subtract the 1, and that leaves us with 60. And dividing these two shows that we have 3 degrees of resolution. So a point at 0 degrees, 3 degrees, 6 degrees, all the way up to 180 degrees for this antenna pattern input file. The same can be done about the values going down the column axis, which represent the phi values, in which case you are doubling everything. You have 360, 120 as your number of points, and again, when you divide those values over each other, you get 36 over 12 is equal to 3 degrees of resolution again. So this kind of is a sort of, I guess you could imagine it's a surface map of the antenna pattern, or the normalized voltage antenna pattern. As you can see, nothing exceeds 1 inside this spreadsheet. So that about covers it for this. Again, there's several ways that you could generate something like this, simulations or what have you. You could probably do something by hand if you bring that resolution down a little bit in case you don't need it. But regardless, that's a general overview of the antenna pattern input file. So next up, we're going to be taking a look at inputting things into the GUI for this problem, and I will see you guys there. Hey everybody, so let's finally take a look at inputting things into the GUI itself for our P-band through forest canopy. So we'll go into SCoBi, source, library, and then we'll run SCoBi. Again, I already have that open, so we're just going to hit run over here. You'll see the simulation selection. We're going to select forest because that's what we're trying to model in this case. And for here, I had a different sort of simulation setup, so I'm going to go and hit load inputs, and I'm going to take a look at default forest because that's really what I wanted to select in the first place. So this should be what you guys have if you have just recently downloaded a clean copy of SCoBi from GitHub. Okay, so again, the campaign name is default forest because that's what we're using, the default input file for a forest problem. The simulation mode is snapshot so that we can get all of those variations that we talked about earlier, those 360 or 80 some odd variations. Our ground cover is vegetation because we're trying to model a forest canopy. These values right here, we're not worried about including in the master simulation folder, and we're not worried about logging the attenuation of those files. For transmitter inputs, we're using a P-band signal of opportunity at 370 megahertz. That satellite is located 42,000 kilometers away from the center of the Earth with an effective isotropic radiated power of 0 dB. The polarization is right-hand circular polarized, and our orientation is changing as we noted in our configuration input file. Our dielectric model is using a Mironov calculating scheme to get the dielectric of our single soil layer profile, and we've denoted that it is single layer through this drop down here. our altitude is 50 meters above the Earth's surface, and our gain is 0 decibels with our polarization again being vertically polarized or expolarized in this case. And our orientation is always going to be following wherever the specular point is. So we're essentially receiving a maximum amount of power, and we're using our antenna pattern that we've created. So configuration inputs file is pointing towards the snapshot single layered varying transmitter file, and our antenna pattern is being used here. Right. Alright, and with all of that, you'll just need to hit run SCoBi, and you should be ready to go, guys.